On September 26, 2022, NASA conducted arguably the most important test they have ever done, and that was Double Asteroid Redirection Test, also known as DART mission. They deliberately crashed a spacecraft worth over $600 million into an asteroid. What is the purpose of it? To see, let's dive right in. Double Asteroid Redirection Test is a NASA space mission aimed at testing a method of planetary defense against near-Earth objects. It was designed to assess how much a spacecraft impact deflects an asteroid through its transfer of momentum when hitting the asteroid head-on. So when the really bad guy shows up, NASA know exactly what they need to do. However, the mission's target was Dimorphos in 65803 Didymos system, a binary asteroid system in which one asteroid is orbited by a smaller one. The primary asteroid Didymos A is about 780 meters or 2,560 feet in diameter. The asteroid moon Dimorphos Didymos B is about 160 meters or 520 feet in diameter in an orbit about 1 kilometer or 0.62 miles from the primary asteroid. DART is a joint project between NASA and the Johns Hopkins Applied Physics Laboratory, or APL. The project was funded through NASA's Planetary Defense Coordination Office, managed by NASA's Planetary Missions Program Office at the Marshall Space Flight Center, and several NASA laboratories and offices provided technical support. International partners, such as the European Space Agency, ESA, Italian Space Agency, ASI, and Japan Aerospace Exploration Agency, JAXA, are contributing to related or subsequent projects. Before year 2014, NASA and the European Space Agency ESA started with individual plans for missions to test asteroid deflection strategies. But by 2015, they struck a collaboration called IDA, or Asteroid Impact and Deflection Assessment, mission involving two separate spacecraft launches that would work in synergy. Under that proposal, the European spacecraft, IM, would have launched in December 2020 and DART in July 2021. IM would have orbited the larger asteroid to study its composition and that of its moon. DART would then kinetically impact the asteroid's moon on September 26, 2022, during a close approach to Earth. In June 2017, NASA approved a move from concept development to the preliminary design phase, and in August 2018, the start of the final design and assembly phase of the mission. On April 11, 2019, NASA announced that a SpaceX Falcon 9 would be used to launch DART. DART impactor designed to be low-cost spacecraft and it had no scientific instruments except secondary spacecraft built by Italian Space Agency for filming the collision of asteroid and impactor spacecraft, had only navigation sensors as Star Tracker, optical navigation sensor called Didymos Reconnaissance and Asteroid Camera for Optical Navigation, or DRACO. DRACO was based on the Long Range Reconnaissance Imager, or LORI, on board New Horizons spacecraft, and supported autonomous navigation to impact the asteroid's moon and its center. The optical part of DRACO was a Ritchie-Chrétien telescope, equipped with telephoto lens with a field of view of 0.29 degrees and a focal length of 2.6208 n/12.16. The spatial resolution of the images taken immediately before the impact are expected to be around 20 centimeters per pixel. The instrument had a mass of 8.66 kilograms. The detector used in the camera was a CMOS image sensor, measuring 2560 by 2160 pixels. The detector records the wavelength range from 0.4 to 1 micron. CMOS detector was used instead of a custom charge-coupled device. In LORRI, as Draco did not require the extreme low-light performance demanded of LORRI during New Horizons Pluto flyby. Draco's detector performance actually met or exceeded that of LORRI because of the improvements in sensor technology in the decades separating the design of LORRI and Draco. Fed into an onboard computer with software descended from anti-missile technology, the Draco images helped DART autonomously guide itself to its crash. The spacecraft solar arrays used a roll-out solar arrays, or ROSA design, that was tested on the International Space Station in June 2017 as part of Expedition 52. Using ROSA as the structure, a small portion of the DART solar array was configured to demonstrate transformational solar array technology, which has very high efficiency SolAero inverted metamorphic (IMM) solar cells and reflective concentrators, providing 3 times more power than current other solar array technology. Also, DART demonstrated the next grid ion thruster, a type of solar electric propulsion. It was powered by 240 square-foot solar arrays to generate the nearly 3.5 kilowatts needed to power the NASA's Next-C engine. Early tests of the ion thruster revealed a reset mode that induced higher current in the spacecraft structure than expected. It was decided not to use the ion thruster further, as the mission could be accomplished without it, using conventional thrusters fueled by the 110 pounds of hydrazine on board. However, the ion thrusters remained available if needed to deal with contingencies, and had DART missed its target, the ion system could have returned DART to Dimorphos 2 years later. Launch preparations for DART began on October 20, 2021, as the spacecraft began fueling at Vandenberg Space Force Base in California. The spacecraft arrived at Vandenberg in early October 2021 after a cross-country drive. DART team members prepared the spacecraft for flight, testing the spacecraft's mechanisms and electrical system, wrapping the final parts in multi-layer insulation blankets, and practicing the launch sequence from both the launch site and the Mission Operations Center at APL. DART headed to the SpaceX Payload Processing Facility on Vandenberg Space Force Base on October 26, 2021. 2 days later, the team received the green light to fill DART's fuel tank with roughly 50 kilograms of hydrazine propellant for spacecraft maneuvers and attitude control. DART also carried about 60 kilograms of xenon for the Next-C ion engine. Engineers loaded the xenon before the spacecraft left APL in early October 2021. Starting on November 10, 2021, engineers mated the spacecraft to the adapter that stacks on top of the SpaceX Falcon 9 launch vehicle. The Falcon 9 rocket without the payload fairing rolled for a static fire and later came back to the processing facility again, where technicians with SpaceX installed the 2 halves of the fairing around the spacecraft over the course of 2 days, the 16th and the 17th of November, inside the SpaceX payload processing facility at Vandenberg Space Force Base, and the ground teams completed a successful flight readiness review later that week with the fairing then attached to the rocket. A day before launch, the launch vehicle rolled out of the hangar and onto the launch pad at Vandenberg Space Launch Complex 4, SLC-4E. From there, it lifted off to begin DART's journey to the Didymos system, and it propelled the spacecraft into space. The DART spacecraft was launched on November 24, 2021, at 6:21 and 2 seconds Universal Time Coordinated. Falcon 9 did almost all of the work, leaving the spacecraft to perform only a few trajectory correction burns with simple chemical thrusters as it homed in on Didymos' moon Dimorphos. The transit phase before impact lasted about 9 months. During its interplanetary travel, the DART spacecraft made a distant flyby of the 578-meter diameter near-Earth asteroid 138971, 2001 CB21 in March 2022. DART passed 0.117 astronomical unit, or 17.5 million kilometers, from 2001 CB21 in its closest approach on March 2, 2022. 2 months before the impact, on July 27, 2022, the Draco camera detected the Didymos system from approximately 32 million kilometers away and started refining its trajectory. The Leisha Cube nanosatellite was released on September 11, 2022, 15 days before the impact. For hours before impact, some 90,000 kilometers away, DART began to operate in complete autonomy under control of its smart navigation guidance system. 3 hours before impact, DART performed an inventory of objects near the target. 90 minutes before the collision, when DART was 38,000 kilometers away from Dimorphos, the final trajectory was established. When DART was 24,000 kilometers away, Dimorphos became discernible through the Draco camera, which then continued to capture images of the asteroid's surface and transmit them in real time. Draco was the only instrument able to provide a detailed view of Dimorphos' surface. The use of DART's thrusters caused vibrations throughout the spacecraft and solar panels, resulting in blurred images. To ensure sharp images, the last trajectory correction was executed 4 minutes before impact, and the thrusters were deactivated afterwards. The impact took place on September 26, 2022, at 23:14 Coordinated Universal Time. The head-on impact of the 500 kilograms DART spacecraft at 6.6 kilometers per second likely imparted an energy of about 11 gigajoules, the equivalent of about 3 tons of TNT, and was expected to reduce the orbital velocity of Dimorphos between 1.75 centimeters per second and 2.54 centimeters per second. The reduction in Dimorphos' orbital velocity brings it closer to Didymos, resulting in the Moon experiencing greater gravitational acceleration and thus a shorter orbital period. The orbital period reduction from the head-on impact serves to facilitate ground-based observations of Dimorphos. An impact to the asteroid's trailing side would instead increase its orbital period towards 12 hours and make it coincide with Earth's day and night cycle, which would limit any single ground-based telescope from observing all orbital phases of Dimorphos nightly. So they have to observe it through DART's companion Leisha Cube, Hubble Space Telescope, James Webb Space Telescope, and the Earth-based Atlas Observatory. On September 26, Southern Astrophysical Research Telescope, or SOAR, observed the visible impact trail to be over 10,000 kilometers long, but scientists estimate that DART's impact displaced over 1 million kilograms of dusty ejecta into space, enough to fill 6 or 7 railcars. The impact targeted the center of Dimorphos and decreased the orbital period, previously 11.92 hours, by roughly 32 minutes. While the orbital change was small, the changes in the velocity, and over the course of years, will accumulate to a large change in position. For a hypothetical Earth-threatening body, even such a tiny change could be sufficient to mitigate or prevent an impact. If applied early enough, it can save a whole life on Earth. As the diameter of Earth is around 13,000 kilometers, a hypothetical asteroid impact could be avoided with as little of a shift as half of that, 6,500 kilometers. A 2 centimeters per second velocity change accumulates to that distance in approximately 10 years. So if you like our video, please consider subscribing. Thank you. See you later.